Je tiens tout d'abord à souhaiter la bienvenue aux membres de notre jury. Et nous avons le plaisir maintenant d'entendre Yusuf Hanka, encadré par le professeur Mohamed Zain et co-encadré par Dr Samir Lemeta, et sera jury par professeur Kishkar et professeur Fatah Al-Akoun et Dr Hanan Belhiraj, et pour un jury présidé par moi-même, professeur Hamza Gbaï, sur le thème Numerical Processing of Nonlinear Frontal Integral Differential Equations by Applying Projection Techniques. Vous avez de 30 à 40 minutes pour présenter l'essentiel de vos travaux. Allez-y.
بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على سيدنا محمد وعلى آله وصحبه أجمعين. نحمد الله سبحانه وتعالى على توفيقه ومنه بإتمام هذه الأطروحة، ومن لم يشكر الناس لم يشكر الله. وقبل بخالص الشكر والتحية بداية بالأستاذ والمؤطر والمشرف الأستاذ محمد زين عيساوي، وكذلك الأستاذ مساعد المؤطر سمير لميطا على دعمهم وعلى إرشاداتهم طوال هذه الدراسة وهذا البحث. وكذلك أتقدم بخالص التحية والشكر لكل أعضاء اللجنة الموقرة، كل باسمه وكل بمقامه، على حضورهم معنا وعلى قبولهم مناقشة هذا العمل. وكذلك أحيي الحضور الكريم الذي أبى إلا أن يحضر معنا هذه المناقشة الطيبة. أبدأ سائلا الله سبحانه وتعالى التوفيق والسداد. The PhD thesis is entitled Numerical Processing of Nonlinear Friedholm Integral Differential Equation by Applying Projection Technique. The outline of this presentation is as follows: introduction and notion preliminary, regular nonlinear Friedholm integral differential equations, and the last one, functional integral differential equation with Caputo-Fabrizio derivative. Let's move on the introduction. Actually, the main focus of this thesis is to present a numerical study for Friedholm integral differential equation. This includes examining both the regular and weakly singular cases, as well as a fractional case. To obtain numerical solution for such equations, we use the popular projection method, like the Gaylord method and the collocation method, along with the classical orthogonal polynomials. So the primary benefit of this approach is that allows us to transfer the main equations for each case into a nonlinear algebraic system. We can then use the iterative method to solve these nonlinear systems efficiently. So to show the accuracy and effectiveness of our approach, we present several numerical examples throughout the thesis. Let's move on to chapter number 1, Notion and Preliminary. In order to provide a comprehensive understanding of the material presented in this thesis, it's important to establish a solid foundation in the relevant mathematical concept. This chapter introduces some fundamental definition and theorem that will be used throughout our work. The first theorem, let K be a non-empty closed convex subset of a Hilbert space H. So for any element U in H, there exists a unique positive, unique point V in K, such that we have equation number 1. The definition number 1, let E be a normal space. A mapping T from E into E is called contraction on E if there exists a positive constant less than 1, such that the equation number 2. Let E be a Banach space and let E be a contraction operator on E. Then T has a unit fixed point x, it means Tx equals x. The definition of Caputo-Fabrizio derivative, let alpha be a real number from the upper interval 0, 1, the definition of the fractional Caputo-Fabrizio derivative of order alpha for a function u in the Sobolev space H1 is as follows. The equation number 3. We defined the Caputo-Fabrizio derivative. Now we define the Caputo-Fabrizio integral. Let alpha be a real number from the interval 0, 1. So we define the fractional integral of order alpha using the Caputo-Fabrizio operator for any function u in H1 as follows. The equation number 4. So we have the following lemma. Given a real number alpha such that alpha between the 0, 1 and a function u in Sobolev space H1, the following equalities hold. Equation number 5. Here, these equalities, the alpha is not the alpha in general cases. This is the minor drawback in the Caputo-Fabrizio derivative. Let's move on to the orthogonal polynomials. The two functions u and v are said to be orthogonal concerning the wide function wz on the interval ab. Question number 6. If we have pi be a family of orthogonal polynomials, then there is a recurrence relation between pn plus 1 pn and pn minus 1. So we have the equation number 7. This equation is very, very important in to define the orthogonal polynomial in MATLAB. Some orthogonal polynomial in MATLAB are defined like Chebyshev polynomial, Legendre polynomial, but general case there is no way to define the orthogonal polynomial in the MATLAB software. This is very, very important to define the orthogonal polynomial in general cases in MATLAB software. The first type of orthogonal polynomial, we have Legendre polynomials. The Legendre polynomials take the following form by the Rodriguez formula, equation number 8. The Legendre polynomials are given from the following recurrence formula, equation number 9. Legendre polynomials are orthogonal on the interval -1 and satisfy the equation number 10. Here some examples for Legendre polynomial, and here the graphical representation for Legendre polynomials for degree between 1 and 4. The second type for orthogonal polynomial, Chebyshev polynomials of the first kind. The Chebyshev polynomials of the first kind are given by the Rodriguez representation, equation number 11. Also, we can define these polynomials. The first kind of Chebyshev polynomials of order n is defined by equation number 12. So the Chebyshev polynomials of the first kind, this kind, can be also defined by the following recurrence relation, equation number 13. And here the graphical representation for Chebyshev polynomials with degree between 1 and 4. These polynomials are orthogonal with respect to the wide function wz and on the interval -1, 1 and satisfy the equation number 14. The third type for orthogonal polynomials, we have Chebyshev polynomials of the second kind. The Chebyshev polynomials of the second kind u and z are given from the following equation number 15. And we can define these polynomials. These polynomials are defined by the following recurrence relation, equation number 16. Adding some Chebyshev polynomials, example for Chebyshev polynomials with n equal 4. And here the graphical representation for Chebyshev polynomials of the second kind. The Chebyshev polynomials of the second kind are orthogonal on the interval -1, 1 with respect to the weight function wz. Furthermore, satisfy the equation number 17. The last type for orthogonal polynomial, we have Hermite polynomials. The Hermite polynomials can be defined by the Rodriguez formula, the equation number 18, and we have the following theorem. The Hermite polynomials satisfy the following form, recurrence relation, equation number 18. And here the graphical representation for Hermite polynomials with degree n and between 0 and between 1 and 4. And here example for Hermite polynomials. These polynomials are orthogonal on the interval L with respect to the weight function wz exponential minus z squared. Moreover, we have the equation number 20. The Rodriguez representation for Laguerre polynomials is the type of Laguerre polynomials. The Rodriguez representation for Laguerre polynomials is equation number 21. Theorem: the Laguerre polynomials satisfy the recurrence relation, equation number 22. And here the 6 of Laguerre polynomials. The Laguerre polynomials are orthogonal with respect to the weight function wz exponential minus z on the interval 0 plus infinity. Moreover, we have the equation number 23. And in the graphical representation for Laguerre polynomials and between 1 and 4. Let's move on to the second chapter. In this chapter, we study regular nonlinear Friedholm integral differential equation. In the first section, we study Friedholm integral differential equation of the first kind, of the first order. In this section, we present both analytical and numerical investigation of Friedholm integral differential equation of this particular type, where k, d, k, dz are continuous function and f, u in H1. This is the main work. We study this equation in the space H1, so model H1, and in the second section we will study in the space H2. But there are articles study similar equation, but in the space C1 and C2. This section aims to investigate the existence and uniqueness of the solution of equation 24 and propose a numerical process for its approximation. So, to achieve this goal, we analyze the necessary condition for the existence and the uniqueness of the solution. Then we apply our numerical method that can approach the solution with a high level of accuracy. Consider the superlevel spaces H1, superlevel space H1, equipped the following norm. As a starting point, let's assume this assumption. So we have this theorem, the equation number 24 admit a unique solution in H based on assumption S. Here several numerical examples are given to demonstrate the efficiency of our proposed method. We mentioned that the numerical results are computed from the following error, such that uz is the exact solution and un is the approximate solution. The numerical result in the tables below are obtained when ck plus 1 minus ck less than epsilon for different values of epsilon. Here the first example, such that the exact solution uz z exponential z, and here the numerical result, the epsilon, the difference between ck plus 1 minus ck, and the degree of the approximate solution. Approximate solution is a polynomial. When we take an epsilon minus 10 power minus 15 and m equal 9, the exact solution and the approximate solution are almost identical. So the error almost nil. And here the second example, such that the exact solution sinus z, and here the numerical result, the error, for example, when we take epsilon 10 power minus 15 and n equal the degree of the polynomial, the exact solution and the approximate solution are almost identical. In that second section, we study second order free-form integral differential equation. Our aim through this section is to introduce a numerical study for this type of integral differential equation of order second order, equation number 25, such that k dz, k d2z, k are continuous function and alpha, beta are real number, phi and phi in H2, so whether space. There are a little article which study this equation or similar equation, but they study over the space C2, not CH2. We utilize Chebyshev wave to obtain an approximate solution, but to improve accuracy, we extend our analysis to a wavelet defined over the sub-interval. We also construct a double operation matrix of integration over different sub-intervals. In the first section, we take the interval 0, 1, but here in the second section, we have two sub-intervals, 0, half, and half 1. We also construct a double operation matrix of integration over different sub-intervals. Finally, we provide several examples to demonstrate the efficiency of our approach. Let's describe our proposed method. Consider the following equation number 26. So we derive the equation 26 twice to get the following equation 27. We approximate the unknown function phi2 prime using Chebyshev polynomial. We get equation 28. Integrating the equation 28 from 0 to z, we find equation number 29. Integrating again this equation from 0 to z, then we obtain the equation number 30. By substituting equation number 28 and 29 and 30 in 27, we obtain equation number 31. Multiplying equation 21 by this equation, this function, we integrate concerning the variable z from 0, 1, then we get the following nonlinear algebraic system. We can solve this system by using Picard successive approximation method. So we obtain the vector solution CP for the system 32. We can subsequently substitute this solution in 30 to get the numerical solution for the main equation 25. Let's introduce the convergence analysis for this study. In order to establish the convergence analysis for the numerical process outlined previously, we begin by considering the superlevel space denoted as H2, equipped with the following norm. Furthermore, we consider the following additional assumption as we have this theorem. Under assumption S, the numerical solution converges into the exact solution in the Hilbert space. Here, the numerical example, the first example, such that the exact solution here, z sinus z, added the numerical result and the degree of the approximate solution, and the error, we get error 10 power minus 5 at 4 degree 3. Added CPU time for run this MATLAB software. Added the second example, and here the numerical result for the second example. The last chapter, fractional integral differential equation with Caputo-Fabrizio derivative. In this chapter, we demonstrate the applicability of our technique in solving fractional integral differential equation with the Fabrizio-Caputo derivative. Especially concentrate on the following equation 33. Dx k are continuous function, alpha between 0, 1, u and g in H1 sublayer space. We explain the construction of the fractional operation matrix of integration, utilizing Hermite wavelet. We then utilize the collocation technique followed by the iterative method to approximate the numerical solution. And finally, to verify the accuracy of our process, we present several examples. Consider the following Friedholm integral differential equation. By taking the derivative of both sides of this equation using the Caputo-Fabrizio derivative of order alpha, we obtain the following result. We approached the unknown function, the alpha u z, by using the equation 31. We get this equation. To approximate the unknown function u z, we perform the integration of 36 with the assistance of the operation matrix of fractional integration mentioned earlier. This process yields EN equal in equation number 37. Substitute this equation in 35, we obtain this equation 38. Use the grid point given as Zi. We apply the collocation to equation 38. This results in the formation of the subsequent nonlinear algebraic system such that data is defined by, and the matrix A is defined as follows. We apply the iterative method to solve the system 39. To do this, we introduce the following system such that dk is defined as follows, and here dEik. So for a suitable value of k, we find the vector ck(t), then substitute this vector in 37 to compute the approximate solution of our equation. And these are illustrated examples, and here the error function such that u is the exact solution, un is the approximate solution. Here the first example, and the exact solution here is sinus z. The fractional order is 0.5. And here the numerical example for this, the numerical result for this example. And here the second example, such that the fractional order 0.75. And here the numerical solution for the second example. And here some basic references. Finally, thank you for your attention.